So you have to say that you accept. And so, Anne, thank you for coming to us. That's a pleasure that you come and bring COVID. Sorry. So thank you very much. It's a real pleasure to see you after all this time. It's a long time ago. And I am happy that you also work with friends from Cyprus. That's really nice to hear that you are very, very efficient and working hard. So please.
Thank you for this very kind introduction, Paul, and also for inviting me. I checked, I wasn't in Paris for almost 10 years now. This is where we met last time here in France, or not in France, we met at Lumini, but in Paris. Yeah, so this the talk about today is about testing equality of spectral density operators for functional linear processes. So we will deal with functional time series, and we are interested in the second order structure of these kind of processes, which is joint work with, as you said, from Cyprus, Santos Kavoditis and Theophanes Sabatinas, and then a former PhD student, Braunschweig, and is now a postdoc in Heidelberg, Daniel Rademacher. So I will start with a motivating example. So I thought that if I come speaking in a seminar of the EcoDev department or as a seminar, maybe it's a good idea to have some temperature data. There's at least some connection to this.
You're welcome. You're welcome to join. Maybe.
And then, okay, then I will give the idea of the problem that we are interested in within this example, and then I want to convince you that having a look at the spectral counterpart of the second order structure of time series is the right thing to do in this specific example, but also for many other applications. I will introduce the test statistic asymptotics as well, but then we will also turn to the bootstrap of this test statistic, because at least in simulation it outperforms the asymptotics, and finally some going back to the example. So what's the example? It's about temperature data. And in this example, we are comparing winters to summers. So I brought two time series. The upper one is Dresden in Germany. So red is 90 summer days, so the temperature reports, and blue the winter. And on the bottom, we have Nicosia and Cyprus. So both of the countries of the authors of this project are included here. And what you see is that obviously the summers are warmer than the winters. This is not what we are interested in, but we are interested in the second order structure, so the variability of these time series. And there seems also to be a difference clearly in the upper picture. In the lower, it's not that clear. In particular, what we see is this daily periodic behavior. So in the night it's cold, during the day becoming warmer and warmer. We see this very much expressed in the summer and on Cyprus also in the winter, but this is deterministic behavior, so this is not what we are going for, but we are more going for the question whether prediction works better in summer or winter, so where's the stochastic variability, where is it higher. So I mean, you see a clear difference in winter and summer for the upper picture, but for the lower it's not so clear, at least from this picture, because this daily pattern somehow dominates the picture. So the idea is to cut this picture into slices of daily temperature curves and interpret these data as functional time series. So now from now on I only have the pictures for Nicosia Cyprus. So actually what we have is measurements every 15 minutes, and then use some Fourier basis to construct this kind of daily temperature curve. So on the left you see the winter, on the right you see the summer, and since this mean is still dominating, we subtract the mean, and then what you get are these curves down here. So you see that there is some kind of a difference between these curves here. They are closer in winter and widespread, more widespread in summer. And we somehow want to understand the difference in the variability in these temperature data. So this is maybe the idea. So to wrap things up is that we now consider temperature curves, that is, we are in the framework of functional time series, to avoid dealing with this periodic daily structure. We will always assume that we are only considering these standard curves, and now whenever it comes to X, you can think of a daily temperature curve in winter and Y, a daily temperature curve in center one in summer. And here are the assumptions that we used in our proof. So the first one is that we assume these processes X and Y to be independent. This is maybe for our application not a big deal, because I mean we have summer and winter and there's a season in between, so this independence assumption is not a big problem here. And we assume that we have this kind of linear structure. So we are working in this L2 space on the unit interval, which is now the rescaled daytime from 0 to 24. And now we have these epsilons here, the innovations, which we assume to be independent. IID means 0. This is just classical, and then we also have the assumption that these quantities of Gaussian.
I just ask you something, because so in fact your temperatures are recorded each hour or something.
Every 5 minutes.
That means you have 24 times 15 times 4. That's 100. But the dimension is like 100.
But if we put everything in the curve, right? So
yes, I know, but
yes.
But in fact, even like that, that means that you have at least models with 100 dimension, and how many years, how many seasons do you have?
We only consider one period in summer and one in winter. So just 96 days is 40%.
Okay. And so with 96 days, you record, you have to fit the time series, which is at least in dimension 100.
So the curve, I mean, what we have is we have here are measurement points, and then we just smooth them using a Fourier basis.
Yes,
and then these 15 minutes times 24 hours are hidden in this, and this small feature comes over these 96 days.
Okay.
As of this. And everything else is hidden in the curve.
Yes.
All of this high dimensionality. Yes.
Sorry.
Okay, so now this is hidden in the curve, and now as we speak about curves, so here in front of this innovations, we do not have matrices as a multivariate time series. We would have, I mean, you would have had a vector process, you could do the same thing, but then you would have a matrix here. So as we do it in the function, we have operators A and B here. And we need some kind of classical assumptions. We need some kind of summability assumptions, as you know, from classical linear processes. So there's nothing special about this, and this is just identification assumption that these operators are the identities. Okay, so far this is all what we need about the model. As I said, there are some restrictive assumptions like that one here, and I will comment on it. We will not need it actually throughout all the proofs, and maybe some part of the proofs can be redone under weaker assumptions, but to keep things explicit and to point out the main ideas, we restricted ourselves to these kind of processes. Okay, then the next thing to do is to define the variabilities or the autocovariance structure for this kind of functional time series. And I have the brief recap here, since I was not sure whether the audience or know about this functional time series. So the point is, I think we are considering the covariance structure of xh and x0 here, and now we have all these intraday times between 0 and 1, and we have to evaluate these quantities at different intraday times. So here and here there can be different numbers for 1 and for 2 within the unit interval. And then the idea is, okay, this gives us the kernel, and then we can define an autocovariance operator of this time series x at leg h by just doing right integration of this kernel small r at leg h. This is the idea. And then, I mean, formulating this test problem that I just introduced before would then be the question whether or not the covariance structure coincides, I mean, for all legs. So this is a very strong null hypothesis that we have here. And the alternative is that there exists at least one leg where these quantities differ. Okay, so this is somehow, I mean, typically there will not be just one leg where this quantity differ when we are under the alternatives. This is somehow then the question how to interpret the results if we are under the alternatives. What can we do with it? And the answer is, let's do it the other way around. Let's have a look at the spectral theory for these kind of functional time series. And I do not want to give a whole theory here. I will just mention the things that we need in our talk for our test statistic. So as I said, no, this is the wrong direction, sorry. The idea is now to get things more interpretable in comparison to using the autocovariance structure itself. And the idea is that we somehow interpret the autocovariance or autocovariance kernel in this function case as a superposition of periodic functions with different frequencies, lambda, and different magnitudes. And then if the null hypothesis is rejected, we will see that the test statistic we are using, we can also trace back the reason or the main reason for the rejection. So the question, is it either due to difference in the long-term behavior or in the short-term behavior? Or in other words, is it due to small or large frequencies? And this is from an applied point of view, an interesting thing to do it this way. Also from a mathematical point of view, one can benefit from this alternative approach. I will tell a little bit about this later when I speak about the test statistic in more detail. So what we want to do is to generalize this concept of using the spectral density. So for the moment, think of real values or univariate time series with an absolutely symmetrical autocovariance function, which I know by RH upper set. And then the spectral density is just this inverse Fourier transform of this covariance kernel here. And there's now one-to-one correspondence. So you can go from the autocovariance function to the spectral density, but also the other way around. So this is where it gets its name from, that you weight this complex exponential by this spectral density and end up with the corresponding autocovariance function. And then you see quite nicely that the idea that we have in mind is nicely represented. So on the left-hand side, we have a process with a rather smooth behavior compared to the right one, which is very fluctuating in a high frequency level. So the left one is AR1 with AR parameter 0.8, this minus 0.8. And you see here the high frequency behavior is dominating. And this is here the corresponding spectral density, and you see the weight is much on the high frequencies there on the left hand side. The weight is large for the small frequencies, and this is the behavior that we later on can also transfer to our temperature data. Okay, so actually there is some work also for this test problem for multivariate time series, not in the functional case, but I and Pavlidis were thinking about this test problem, and now we want to generalize this to functional cases. And this is the way okay, this is the way how we go on. So what we do here is, I mean, basically using this definition of the spectral density that you just saw on the previous slide, but now we do it on the level of kernels. So what you have here is, or again, these intraday times in the arguments of our autocovariance here, and now you have the same arguments just driving through this formula also for the spectral density, which gives you then a spectral density kernel for every frequency lambda in this interval minus pi. And then the corresponding operator again achieved by right integration of this kernel, we call spectral
density. That's a matrix effect. It could be seen as a matrix also. It's a matrix spectral density.
Yeah, I mean you are not on the discrete.
Yes, I know.
But in a sense, yes, I mean it's just a generalization. And you can show, which was done, for instance, in this paper here by Panaretos and Tabacoli, that this function is well defined, so it converges to the inversion formula holds again, and the operator has nice properties that help you improve. And we are now able to reformulate our test problem in terms of the spectral density operator, namely under the null hypothesis. We assume these operators to be equal while for almost all frequencies, while under the alternative, we assume that there is a set of positive Lebesgue measure where these operators differ. Okay, and if one wants now to do the test statistic comparing the spectral density operators of the x and the y time series, we need estimators for these quantities. And then the idea is again to use the kernel approach, first defining periodograms. Again, in this kernel version here, which I denote by P in this talk. And as it is known from univariate or multivariate time series, this is not a consistent estimator for the spectral density. We need to do some smoothing. For instance, here we use some kernel type of smoothing. We introduce the kernel function, and we now evaluate the spectral density, the periodogram at the Fourier frequencies, which I denote by lambda t. So this is 2 pi t over capital T, so the sample size capital T. And then we put a weight function W here, giving higher weights if lambda is close to this lambda t, and the bandwidth parameter P, so just the usual non-parametric thing we are doing here. And then we are going over all Fourier frequencies within the interval minus pi. This is we go from minus n to n, where n is t minus 1 over 2. And using this quantity, we can then define a spectral density, or the estimated spectral density operator the same way as we did all the things before. And then we can use these quantities now to build up our test statistic. I will not speak about properties, asymptotic or non-asymptotic here, but I just give the references if you are interested in these kind of results, interest rates and so on and so forth. Instead, I want to go for the test statistic and its asymptotics. So here's the test statistic, or the test problem first again. And then if you have a look into the literature, there's a projection-based approach for fixed frequencies by Tabacoli and Panaretos, which is obviously not consistent against all alternatives. It's totally set projections. And here we wanted to evaluate really all frequencies. And just compare the Hilbert-Schmidt distance between the estimated spectral density operators of the x and the y time series, and then integrate this squared Hilbert-Schmidt distance with respect to the frequency. And then this is also numerically feasible, since you can write this Hilbert-Schmidt distance as the integral over the distance of the corresponding kernels, which we can calculate. Actually, there's related work for testing relevant hypothesis. So what's relevant hypothesis? Here we are testing whether the spectral density operators are equal, which is a very strong null hypothesis. Alternatively, we could also ask whether these guys are close together with respect to this distance over there, and fix a threshold. And so the null hypothesis would then be that these quantities are close or not exceeding a threshold. And this is what is done by Anne van Dette in a related paper. However, the asymptotics for these kind of statistics are completely different than ours, because the dominating terms are different from these statistics, and therefore the methods cannot be just substituted from going from one problem to the other. Okay, so here's now the main results regarding the asymptotics of the test statistics. So we need some bandwidth assumption which I denote by I here, and then another assumption on the kernel. I mean, these are just classical assumptions, so there's nothing special about these. Actually, they are the same as they were used in multivariate time series, so we cannot pay a price with regard to assumptions on the bandwidth, for instance, going to the infinite dimensional case. And then one can show if we suitably center our test statistics, we end up with asymptotically with a normal distribution, which is however not standardized, but has another variance term. So you see that the mean and the variance term here. So the point that I want to make is that both depend on this spectral density operator fx, which is unknown. So we cannot use directly this result to derive critical values unless we estimate these quantities, mu naught and beta naught. We will tell you a little bit more about this on the next slide. And under the alternative, the test statistic also after this normalization will explode. So this is what we will use later on when we set up our bootstrap approach.
Sorry,
Should I go back?
What is W? It's
the W is the weight function, the kernel function.
Okay, sorry.
Okay, so now we discussed a little bit already why we use linear processes in advance. So the basic ideas of the whole audience, I will repeat our discussion a little bit. The basic idea is that we can trace back the periodogram of the linear process to the periodogram of the innovations, which are now assumed to be independent and Gaussian. And under this assumption, one knows that the periodograms at different frequencies are independent. And then basically the test statistic is traced back to weight squared form of the periodograms of these innovation terms of the epsilons here, which we have to deal with. And it's easy if these periodograms are independent of each other, then we can use a simple limit theorem for quadratic forms by de Jong. And this is why we use Gaussianity and these linear processes. Probably one could also work under cumulative assumption, as for instance in this paper, they do not go for linear processes. In particular, when we wanted to derive this centering and this variance term, we only need 8 moments, but no Gaussianity or linearity in that group. Okay, so this makes just our lives easier. Now, how can we build a real test out of the asymptotics that we got? So we, as I said, we have to standardize statistic to use the quantize of the standard normal distribution for the or as critical values. And therefore, we have to find estimators for mu naught and sigma naught, which depended on this unknown spectral density estimator of x. And actually, what you have to use is not an estimator of the spectral density kernel fx lambda, but of a linear combination of that one and the corresponding one with y. Because you have to be sure that everything also works under the alternative, so that the standardization does still not disturb the behavior, this exploding behavior of the test statistic under the alternative. And for that reason, you have to use this pooled estimator, which will also pop up later on the bootstrap slide. So on the null hypothesis, actually, I call this F lambda now, this pooled spectral density estimator. It's just the same as using Fx, so everything is fine under the null. We end up with the desired quantity as before, but we also take care of the alternative. This is the way you have to do it. Okay. So basically, I could stop here because I mean we found a solution, but the point is that normal approximation for this kind of two-type statistics is rather poor. So what you see here is in red is the estimated density of the test statistic for sample size 500, and the black line is the corresponding normal distribution. And you see there's some space for improvement there and here as well. So the question is, can we do better using the bootstrap? And I will show you later on also some estimated densities of the bootstrap counterparts of the test statistic, and you will see that we are doing much better than with this normal approximation. So basically, there are two main issues that we have to face here, or we have to tackle here. So first of all, we have the dependence structure in this data, as we use linear processes, and we have this infinite dimensionality. And the idea is for the bootstrap, not to bootstrap the data themselves, but to bootstrap the discrete Fourier transforms of these quantities, or what I call the building blocks of the periodogram I know by J here. So J is the Fourier transform of the X process at certain sampling points. So previously there was a sigma or tau here, now I write as J for the sampling point. So we do this now at finitely many sampling points, and for finitely many such frequencies lambda. So later on we will just use the Fourier frequencies. And now it is shown in this paper by Zerovicki and Hermann that these guys are asymptotically complex normal. And also if you evaluate these quantities at different frequencies, these ones are asymptotically independent. And this gives the idea for the following bootstrap algorithm. So whenever we take Fourier frequencies which are not zero, we can use just this complex normal distribution. Actually, the variance or covariance matrix here is just, I did not explain it on the previous slide, because we cannot see it here. It's just built out of the spectral density kernel at these sampling points. So the idea is now to construct bootstrap J's, so to say, using this complex normal distribution where we plug in an estimator for sigma lambda here. And and we have to take care again that our bootstrap works under the null and under the alternative as well. So we have to again use the pooled spectral density operator, because we want that our bootstrap imitates the null also if the data do not follow the null hypothesis. And this is how we take care of that. And then we just can go on and putting things together. So by definition, the periodogram is just this J times J complex conjugate for all of these Fourier frequencies with the T equal from 1 to n. For the negative indices, we just use properties of the periodogram, so a kind of symmetry here is just minus lambda at this point. And then we plug everything into our spectral density operator, doing the kernel weighting. And then we plug everything into the bootstrap statistic. So this one's a bit different than the one you saw on the original side. This is for two reasons. One reason is that we do not have the interval 0, 1, but only sampling points S1 to Sk here. So instead of the interval from 0 to 1, we have the sum here. And also for the frequencies, we do not evaluate the bootstrap statistic at all frequencies, but only at the Fourier frequencies. This is what we do. And if we then do the same kind of standardization, we end up with the bootstrap statistic and would reject the null original statistic exceeds the critical values obtained by this bootstrap procedure. Maybe one word about these sampling points. So actually, typically, as also in our application in the beginning, we do not observe really functions, but we observe these functions only at a finite grid, and this grid, so in our case was this 15-minute records of the temperature, and one could choose these grid also now to define the sampling points of the bootstrap site to be somehow consistent with what you observe from the data. And then, I mean, in principle, you could transform these variables to functional objects using 3 bases or something like this. And then if you would increase the number of sampling points, you would basically come arbitrarily close to this quantity down here, where you now again have the integral with respect to the intraday times, but still only sum over the full frequencies. And actually, for this quantity, we proved bootstrap consistency, as you can see it on this slide. So under our assumptions that you saw before, again, we get asymptotic normality of the bootstrap test statistic now under the null and under the alternative. So both under both scenarios. And you see now here in the centering and the variance is slightly different. So because here now you have this pooled spectral density operator in this mu tilde and the sigma naught tilde, and under the null hypothesis, this just breaks down to fx as before. So you really imitate the right limit distribution under the null. Under the alternative, you still imitate the standard normal. Sorry, the square should be here inside. So this is really normal distribution now. Okay. So you really imitate this scenario under the null, and under the alternative, you have a standard normal variable while your original test statistic explodes, so we get consistency of the test. And as Paul was quite critical about our linearity assumption, so this is actually you do not need a linearity to prove this bootstrap part. You mainly have to be sure that your spectral density estimator behaves nicely in this sense, and actually this is the case for the linear processes under some mobility conditions on these coefficients, but also for other kind of dependent structure, physical dependence or something like weak dependence. You can also prove
this is A1 actually.
A1 is the condition saying that our processes are linear processes.
Okay.
And this is, we need independence still of this X and the Y process, but no longer this linear structure.
It's a kind of regularity condition, but right?
Yes.
This is a regularity condition.
Yes.
And
so on the bootstrap side, this is enough. You basically, you already have that these J's are already normal, they are already independent. So all these things that you had to figure out on the original side are already done by construction of the bootstrap method. But on the bootstrap side, you plug in not the true spectral density operators, but the estimators, and you have to take care that this estimation effect is not dominating.
And the only condition was the solvability there was a solvability condition of the
for the linear
the norms.
Yeah.
And if you change this for something a bit more like there was a sum of something b times the norms.
Yeah.
If you change it to something more like b at the power some power, so it's a higher regularity condition, then you don't improve the results. You get that's in fact what I have in mind. I will ignore both sides.
Shall I go back to the assumption?
Yes, please.
That one. So you mean this is
no, before. Before. Yes, here.
If you increase this, I think you have to change the reality, and then you should get this.
So if you increase the norms condition, do you get something better or not?
Then this square would be, you mean?
Yes. Because in fact, in a sense, what I feel is that something like this is a regularity condition, and when the regularity increases in functional estimation questions,
yes,
you relax some conditions. That's what I say, and that's a way to feel differently the exact situation between
I understand
the
I'm not quite sure. Because I'm not sure whether they really increase the rate that much of you. So you would get rid of, I mean, you want to have another power of B in this
Yes,
condition. This is what they mean. Probably it is like this, yes.
In fact, the question is whether you can, if you just have more, as you said, if you improve if you put more times, then what happens? If you put more times of observations,
so within a day,
then you approximate better the functions, and does it change something or not?
This is a different question if you put more, because in this condition that you saw on the previous the slide, you have already the integral over all frequency, over all intraday time. So you basically assume that you observe the whole curve. So whenever putting this assumption down here, we are assuming that we observe the whole curve. This measurement error that we have, I mean, by smoothing the curve to data points is not included here. We already assume that we have the whole curve. But there is some theory in this paper by Canaretos and Cavacoli where they consider what is or which rates we lose if we have this grids going from the grid to the whole curve. So in their paper they discuss these kind of things. We skip them here, as we only consider, I mean, this UT is that one here where we already have the integrals.
Did you compare with high dimensional alternatives?
No, we did not. So you think of high dimensional matrix?
Yes.
Also, we did not do simulations, but I think the results are pretty nice because, I mean,
so this is sorry, this is a MR2.
MR2, yes. Just to get the simulations run quickly. So we have really a functional part here. So here we have a kernel operator A1, and then we have a scalar A2, which is not appearing for the Y process, which means if A2 is 0, the X and the Y have the same covariance.
What is A1? I'm sorry.
A1 is a Gaussian kernel operator.
Okay.
And now if you increase A2, you go more and more deeper into the alternative, so to speak. And then the power should increase, right? And so, but what I pretty much like are these pictures here because they show that the normal approximation is really bad. I mean, I do not know whether you see the red curve. It's here in the blue ones. So you're really doing much better with the picture imitating the test statistics. So the left-hand side is a sample size 50. So really small samples, although beyond this functional context, and the right one is just the picture that I showed you before, the sample size 500, and I also brought some of these ugly tables. So the first line is whether it's under the null hypothesis, so at different levels, and you see already for the small sample size, we keep the level very nice, but of course we lose it in terms of power compared to larger sample. But still, I mean, it's only 100 for these functional objects. I think it's not too bad. Actually, what I did not speak about is the bandwidth parameters so far. So actually, what we did is for our data applications, we used the following approach. We had to look into the literature, and there's a paper by Robinson who's discussing multivariate time series. And they proposed some kind of cross-validation approach to tackle the problem of finding the optimal bandwidth, where they also show some kind of optimality property. And now here we adapted this approach to the pooled periodogram average over a discrete set of these sampling points to get things done, to get rid of this high dimensionality which we would otherwise face. So basically, you can interpret this quantity as the periodogram of this integrated process, and then the corresponding full spectral density operator, now full over all these, also over all these sampling points, is denoted by G hat, and this cross-validation approach is such that you minimize this kind of pseudo maximum likelihood approach, maybe so to say. So you have the periodogram here, and then you have these smooth estimators where you always skip the t's Fourier frequency here when you do this weighting, so you skip t and minus t, and then you have this kind of leave one or actually two out kernel estimator for these frequencies, and then you can do some kind of cross-validation.
There are theoretical results for this?
In this paper for Robinson, that is for the
yes.
For the univariate case, for sure. For the multivariate case, if I remember correctly, he also uses this kind of averaging. And yes, in this paper, we did not do any theory on that.
And thank you. Oh, sorry. Just maybe I shouldn't ask so many questions, but you use what the distance between spectral density operators is it's did you think of others?
No, we did not think of others, because Schmidt.
This is nice to write because of
yes,
the representation.
Yes, this is the true, the honest answer to that. And also, simulation results were not too bad, so therefore we stick to that.
Okay.
So in the end, we come back to the original example of testing whether we have a difference in summer and in winter for our for our temperature data. We use this bandwidth selection procedure that I just mentioned, and I give you here the p-values for Nicosia and for Dresden. So in Dresden, we already saw from the picture that there's some difference going on. So the p-value is quite small, and then so the rejection of a null is, I wrote it most of the classical levels.
So in Dresden there is summer and winter.
Yeah, Nicosia is not that, it's not that bad. Actually, so this is what I said. I want to use this test statistic. I mean, we integrate over the intraday times and we integrate over the frequencies. And now we could think of only integrating one of these dimensions out and to see what is happening. And so I brought the plots for Nicosia, but actually they look quite similar for Dresden. So here on the left-hand side, we have a look at which frequency gives most weight to the or contributes most to the test statistic, and you see that. So this is on log scale. So we fix the frequencies and calculate this Hilbert-Schmidt distance for different frequencies, and we see that the small frequencies give the highest weight. So this means the long-term behavior is dominating, or is dominating in sense of the difference between these both time series. So we have more stability in summer than in winter. So this is how you can explain this. On the other hand, if you do the other way around, so you integrate out overall frequencies, or this is summing overall frequencies on the bootstrap side, but now you fix the interday times. So this is this table here, and so the dark parts are the parts where there's a high difference in the variability. So in the afternoons, we have more variability in summer than in winter. This is due to the fact that if the weather is cloudy or not cloudy, this has more effect in the summer than in winter, especially in Dresden always. And so this is what I pretty much like about this test statistic, that you can do some further analysis beyond going to say that the null hypothesis is rejected, because I mean, I guess that this is much.
Did you build procedures that's easy to run those things?
This code, I mean, we have the code ready now, so
because I would like to suggest you something is that in fact you could even think about discussing a bit the global warming question by considering various
Okay,
Yes.
but then we would, then things are much more complicated, then we would have to go to, say, locally stationary time series, something like this, because then we have.
Yes, but
Well,
on the year, I can think about stationary and try to just consider over years if there is a change.
Yes, we could do this. I mean, yes, this is maybe a very good idea to, global warming is not just in mean, but also the, as it is said, always with the variability does
It would be
change.
I am sure that Federico would be very interested about it.
Yes, maybe I didn't catch very well the results of the empirical application. So you focus in the year 2007, considering observation in winter and observation in summer. But at the end, what is the result of your test in meteorological terms?
So the result is, I mean, you could say that weather forecast in winter is more difficult than in summer, as there's a higher variability if you go for the long-term behavior. For the intraday behavior, it would mean just the other way around, since the variability in summer is higher, for the afternoons it's harder to forecast. So in this term, we can evaluate this variability here. Or as Paul suggested, we could also test for whether the variability is changing from going 10 years back to the current time.
And this is valid only for 2007, obviously. Obviously, no? Is valid only for 2007, obviously. Yes. So I think that you can have some conclusion in terms of climate change if you enlarge your analysis by considering always an analysis focusing just on 1 year. But if you repeat the analysis for the length of 30 years, and then you compare the results, then you can have some you can extract some conclusion about evolution of climate change. Maybe if you have enough data. This is always the problem.
Yes, I completely agree.
In fact, there is
but there was data, but so actually this is why I choose Dresden and not Bamberg, where I'm actually located, because I did not get the data for Bamberg, and I also not sure how many years back I can go for this.
In fact, there is something I would like to say about the methodology. There was a very nice talk by Denis Pomeroy, who was comparing things, couples of things. So in this case, you would have to compare years, by couples. So you compare couples by couples, and there was a nice methodology to make it sure that there is a chance that if all the years are equal or not, something like that.
So there's
and
more
that
like a
there is a technique of considering convenient couples, and it was really nice. You could go and see the result.
So this is also on the ECODEP seminar.
No, I think it would be nice. There is maybe some combination of those things to check.
Yes, thank you very much for your comments.
So maybe we stop recording. I think. Okay, we stop recording. Okay, and thank you. We didn't thank you. Thank you very much. It was very nice, and I got